Let's begin by considering this question. This is a hotly debated topic on cold nights. If you were to open the window on a cold day, are you letting the cold air in or are you letting the warm air out? By the end of this lesson, you should be able to answer this question. And the next time this is debated amongst friends, you'll be able to chime in with a scientific answer here. In this lesson, we're going to look at calorimetry. Calorimetry is a tool that we use in chemistry. We can do quite a bit with this tool, and we're going to begin by looking at the first law of thermodynamics, which states energy cannot be created or destroyed, only transferred. Right, that's very important. Heat's going to flow from the hotter object to the cooler object. So thinking back to the opener here, I asked, is the cold air coming in or is the warm air going out? Okay, so according to the first law of thermodynamics, we know that energy can't be created or destroyed. Heat is actually going to flow from inside our warm house outside into the cold environment. So that cold air that you feel is basically just the warm energy, the heat leaving your room. Heat stops flowing when both objects reach the same temperature. So we're going to be working through a lab where we're going to be finding the specific heat of a metal. So we're going to have a warm metal and we are going to put it into colder water, and you will see that the temperature of the water will start to increase. It will eventually taper off. So the temperature will start to increase and then it will taper off. So when we reach this point where the temperature starts to taper off, we know that both objects have reached the same temperature or equilibrium. So all of the heat energy from the metal is going to be transferred to the water. Now this is key. So our metal is going to be losing heat energy, so it's going to have a negative Q value. The water is going to be gaining energy, so it's going to have a positive Q value. All right, let's look at an example. You have a 75-gram sample of metal and it's heated to 100 degrees Celsius, and it's placed in a container holding 100 grams of water at 24.4 degrees Celsius. The contents of the calorimeter come to a final temperature at 34.9 degrees Celsius. The specific heat of water is 4.18 joules over grams degrees Celsius. Calculate the specific heat of metal. This is exactly what we're going to do in the lab. There's a lot of information in the question here, and what I'd like to do first is kind of put everything into a table. So we have our metal. All right. We know the mass of our metal is 75 grams. We do not know the specific heat of our metal. The initial temperature of our metal is 100 degrees Celsius, and the final temperature of our metal is 34.9 degrees Celsius. So our change in temperature, so 34.9 minus 100 gives us a change in temperature of negative 65.1. All right, our water, the mass of our water is 100 grams. The specific heat of our water, given in the question, is 4.18 joules over grams degrees Celsius. The initial temperature of our water is 24.4 degrees Celsius. The ending temperature of our water is 34.9 degrees Celsius. So just like before, our final temperature, 34.9 minus 24.2 equals 10.5. So our delta T here is 10.5 degrees Celsius. So using the equation on the previous slide, I'm going to write that out. So we have negative mc delta T, and this is for our metal, is equal to mc delta T for our water. So now it's just a matter of plugging in everything that we have. So negative 75 grams of water We don't know the C value, specific heat. Negative 65.1 degrees Celsius is the change in temperature. And that's going to be equal to 100 grams of water, the specific heat of water, times the change in temperature, which is 10.5. So when we multiply this all out, I get 4,882.5 C on the left. On the right, when I simplify everything, I get 4,389. And then I want to divide both sides by the 4,882.5. And I get a final value, a specific heat of my metal of 0.899 joules over grams degrees Celsius. So in the question, we were not given the specific heat of the metal. We were given all of the information about our water. The only thing missing from our metal was the specific heat. So we were able to set this up and solve for our specific heat. And this is exactly what you're going to be doing in the lab.